This is the third lecture on non-local minimal surfaces. Today I'll continue talking about some properties on the regularity of non-local minimal surfaces and mention some differences, with the local case, something that is unexpected, a few things that are unexpected in this setting. Okay, so let me remind you that we look at non-local minimal surfaces. These are boundaries of measurable sets E, and that minimize the perimeter. The perimeter is the HS/2 norm of the characteristic function of E restricted to the domain omega, which amounts to basically integrating all x in E and all y's outside of E relative to this kernel that appears in the fractional Laplace. And we say that E is a minimizer if the perimeter is the least among all perturbations, all other sets F that coincides with the outside. And sometimes I call E a non-local minimal set, or I say that the boundary of E is an S non-local minimal surface. Yeah? As I mentioned the other time, E is not, if I take the complement of E everywhere, that would still be a non-local minimal set. So really the boundary of E is the one that is important. Okay, and what did we cover so far? So last time we talked about lower semi-continuity of the perimeter, which allows us to prove existence. Also we have compactness of minimizers, meaning you give me a sequence of minimizers, and also the boundary data outside of omega, they converge to some limiting set, and then the limiting set is also a minimizer. We have these density estimates that tell us that points on these non-local minimal surfaces, if we center balls on the boundary of non-local minimal surfaces, we see always a fixed proportion in the set E and also a fixed proportion in terms of density in the complement of E. Last time we also said something about the Euler Lagrange equation. If we assume we have some regularity here, let's say if we assume that the boundary of E is smooth, is C2, then we can say that the S non-local mean curvature is 0. And this can also be understood in the viscosity sense. We don't really need that the boundary of E has to be smooth. It's enough to have a one-sided bound. If we have a tangent ball from one side, then we get an inequality here. If we have a tangent ball from the opposite side, then we get the opposite inequality. Yeah? But if we are C2, we always, at any point, we have a tangent ball from one side and the other. So this would be the Euler Lagrange equation. And last time we also mentioned the extension problem. So if you give me a non-local minimal set E, then there is, we can construct the extension of this function, where I put a 1 in the set E and a -1 on the complement. And I look at the extension problem, I call this capital U. And it turns out that if U is a minimizer of this norm, right, which means if it's a non-local minimal set, when we minimize this norm, we only minimize it among functions that take values 1 and -1, characteristic functions of sets F just like this. It turns out that U is a minimizer of this Dirichlet energy in the extension problem among all compact perturbations of U, but these compact perturbations actually are allowed to touch the boundary as long as on the boundary I still keep the values 1 and -1. Yeah? So when I say we minimize this energy, we understand not only on compact perturbation in Rn+1, right, but this compact perturbation, let me draw the picture. Yeah? So we have our Rn here, and we have some set, and then let's say that this is our omega. Yeah? Then when we build the extension, I can take here any domain, and I'm looking, if I take a capital V that is equal to U on the outer boundary, yeah? However, inside of omega, I can take capital V to be the characteristic function of another set F minus the complement. Yeah? Then the energy of U would always be less than the energy of V. Yeah? So compact perturbations are allowed to touch the bottom of Rn in omega, only in omega. Outside of omega, I have to keep things the same as long as I keep the same values. Yeah? So that's how minimality looks in the extension variable, we do it for the extension function. Okay, so why do we care about the extension? I only briefly mentioned it last time, but this is a crucial ingredient in the theory, the monotonicity formula. So the monotonicity formula tells you that a certain quantity is monotone in R. What is the quantity? So the quantity, we look at the energy, the energy of the extension in the ball of radius R, and rescaled properly. So all this quantity is scale invariant. So if I keep the same values of capital U and I dilate from the ball of radius R to the ball of radius 1, then this thing here is simply the energy, what I see in the ball of radius 1, yeah, under the natural rescaling. And the monotonicity formula says that this function is monotone in R. Yeah? And is constant in R only if the function capital U is homogeneous, zero homogeneous, meaning is constant on rays. Yeah? So on each ray is constant, in particular on the bottom, if also the characteristic function is to be constant on ray, which means that the set E itself has to be a cone. And the important part of the monotonicity formula is this characterization, because in the limit, if you have any function here and you say, let's look closer and closer and closer, the monotonicity of this quantity tells you that you have a limit when you zoom in, and in the limit, this quantity has to remain constant for the limit, and therefore the limit has to be zero homogeneous. Yeah? So the key of the monotonicity formula, it tells you that when you blow up, when you look close, when you zoom in, the limit has to, up to subsequences, yeah? I mean, this is a convergence up to subsequences. You zoom in, you extract a convergent subsequence, but that limit has to be zero homogeneous. And this is the place where you see the extension is very useful, because the extension, once I step from the plate a little bit inside, right, the value of U at that point is influenced by the values of U on the bottom in the whole space. Yeah? So this function capital U contains information from the bottom data from everywhere. However, in the monotonicity formula, this is like a local quantity. I just look at this integral in BR plus. It seems that you forgot what happens outside of BR. You didn't forget because you include values of the extension inside this ball that carry the information from everywhere in the space. Okay. So how do we, let me just, the proof is very easy of this monotonicity formula, but as I said, if you wouldn't do the extension variable, I don't know how to do it. I mean, it's not clear what the monotonicity formula would look like. Of course, you can translate this, but you'd get a double integral that seems very arbitrary. I mean, not intuitive. Why would you take that quantity? Okay. So let's say, are there some questions so far? So the proof is very simple. We just try to differentiate this and say we would try to prove that the derivative has a sign. So when we differentiate, let's assume we fix a ball like r equal to 1. We differentiate, and we have one time we can differentiate the integral, right? If we differentiate the integral, we get this term, which is, right, there are two terms here, right? R to the 2s minus n, and the integral on the solid half ball. So when I differentiate the integral on the solid half ball, I get this boundary, integral on the boundary, on the spherical cap. And then I have to subtract this constant n minus s that comes from differentiating r, that's the scaling factor, and then back the full integral. So this is the derivative. Yeah? Now I build a comparator in the extended variable u tilde, which has the same values of u on the, let's see, on the top half ball. So I'll draw a picture here. So we have the half ball of radius 1, yeah, like this. So I have the function u defined here. And then I define sort of a comparator u tilde in which I take the value of u here, but I extend it constantly to the origin. Yeah, in particular, also the set that I see here, I just... So I keep the same boundary data on the upper ball, because that's what I do, right? On the bottom, I sort of modify it, but I still have only values 1 and -1, because on the bottom, I extend the value of my trace that I see on this circle, and I copy that on the whole ray. Yeah? So this is an admissible comparator. Yeah? So the energy of u tilde is this deformation of u. I know that it's supposed to be less than the energy of u. Okay, so that's what is written here. What's written on the bottom is that the energy of u in the half ball is less than the energy of u tilde. Yeah? And here I'm using sort of minimality of u. If I look at the energy of u just on the half ball, or on the half sphere, yeah, actually this is bigger than the energy of u tilde on the half sphere. Why? Because tangentially they have the same values, but normally u tilde is constant. So actually I have no normal derivative. The normal derivative is 0, while u has some derivative there. So this is again a clear inequality, which tells me that if instead of u here I plug u tilde, right, I'm going to get something less, because this gets smaller while this gets bigger. Yeah? On the other hand, the energy of u tilde, the energy of u tilde is invariant, when I zoom in, is invariant under radius, because u is simply homogeneous of degree 0. Yeah? So what I get, I get that the derivative of phi of u is bigger than this for u tilde, which is the same as the derivative of this quantity of the monotonicity formula if instead of u I plug u tilde, but this is 0. This is 0 because u tilde is homogeneous of degree 0 and is scale invariant. Yeah. So this is the proof, right? I mean, it's like a one-line proof that says that this quantity remains monotone. I mean, this derivative is positive. When do we have equality? So we have equality exactly when I said, right? So if I look at this inequality here, I needed to have equality, which essentially tells you that on this radii, I want the normal derivative of capital U to be 0, to coincide with the derivative of u tilde, which says that your function, if I have equality all the time, your function has to be constant on rays. So u has to be constant in the radial direction. Okay, so this is the proof. It's very simple. What are some consequences of the monotonicity formula? So the consequence, I already mentioned them, but let me say again. So if E is a non-local minimal set, and let's say 0 is the point on these non-local minimal surfaces, then if I take a sequence of lambda k tending to 0 and I want to scale Like I want to make the ball of radius lambda k to be back the ball of radius 1. So I just do a dilation, right? So my set E dilates like this, right? And I say I can find a sequence of dilations that has to converge to some limiting set E in the whole space now, because even if your function originally is a minimizer in the domain omega, when you zoom in, this domain omega tends to infinity. So in the end, you end up with some convergence in the whole space, and this E bar is going to be a minimizer. This is from the compactness of minimizer, yeah? And also you get that the extended function converges to the extended function of this E bar, and this E bar and U are zero homogeneous, yeah? So in the end, you get this picture on the bottom when you zoom in near a point, yeah? So you think I have a set here I have a minimal set here that looks like this, right? And you pick a point. When I zoom in more and more and more and more, I expect what? Well, maybe I expect, right, this picture. Like a cone. Of course, in most of the places, when you zoom in, you get a cone, but which would be the trivial cone. The trivial cone is E on one side of a hyperplane and the complement of E on the other side. Yeah? So you expect to see this picture at most of the places, generically. Yeah? But sometimes you might see some pictures like this. So that's why it's very important to understand what sort of possible homogeneous of degree 0 minimal surfaces are there. If you understand all these situations, all the possible cones, then you have a very good idea about the regularity of the set E, of the minimal surface. Okay. So, yeah, so let's... Okay, so the next thing that I want to talk about is something that is called improvement of flatness, which says that, let's assume I'm at the origin and I zoom in and I zoom in and I zoom in and I end up in this situation. Yeah? If I zoom in and zoom in and I end up in the situation that the blow-up picture is a half plane, what it tells me that the original picture that I start with at some point is very close to this when I zoom in, right? That's what I converge to this, but I'm not exactly that, yeah? So you say if I have a set E that is very close to half a plane, what do I mean by very close? So inside the unit ball, if I can say that the boundary of E is trapped in a band of with epsilon 0 being a tiny constant, then I can guarantee that actually the boundary of E is smooth inside. This is a graph of a C1 alpha function. Yeah? So this is the place in which you really go from, I don't have too much information about E, it's just a measurable set. I go from being just some measurable set to being a graph of a function. Yeah? Of course, under what hypothesis? Under the hypothesis that I'm sufficiently close to this situation when I look closer and closer and closer. Okay. So I don't have time to go through the proof of this, but it's in the notes. If you check the notes that I sent, the proof is there. And I just want to mention something. So how do we prove this? So there is this lemma, this proposition, which says more or less, let's assume that the boundary of E is only a viscosity solution. So I'm not, what I want to insist here, that in this proposition you don't assume minimality. You only say, let's assume that the boundary of E satisfies the mean curvature equal to 0. Yeah? And let's assume that E is trapped between, in a ball of radius r, is trapped between two planes, at distance r to the 1 plus alpha. This would tell you that essentially when you zoom in, r goes diagonally. Yeah, so say you look at the surface, and initially as you zoom in and you zoom in and you zoom in, you see that you can trap your surface in planes that are closer and closer and closer relative to the radius, right? If I look at the distance between the hyperplanes relative to the radius, is decaying also geometrically. Okay? Well, it says, this proposition says that if I see this for k equal to 0, 1 to up to some certain k0 sufficiently large, then I'm going to know it for all k. Yeah? So this is some sort of non-local effect. So here I show some pictures saying that let's assume that in B1 my surface is trapped in this cylinder. When I go to B1 half, it's trapped on a flatter cylinder. When I go to B1 quarter, in a flatter cylinder, and so on. If I know this for 1,000 times, then I can keep on continuing this. I can deduce it that it holds for all k's. So this improvement of, that's why it's called improvement of flatness, because the flatness is the ratio, is the flatness of the cylinder, and as you zoom in, you keep on having this geometric decay of this flatness. Okay. And somehow, why do you need it? Why you cannot say it right from the beginning, right? You need, in general, when you deal with non-local equation, if you just to tell me that I know how the set E looks in B1 is still not good enough, because the outside has some influence. Yeah? And on the other hand, if I have information on E on some large set between B1 and, I don't know, B a million, then I can start concluding something better and better in B1. Yeah? So this is a difference with respect to the local theory. And I don't have time, as I said, to go through the proof, but the key idea is to say, let's assume that the boundary of E is given by a graph. Yeah? If the boundary of E is given by a graph, you think the graph is epsilon, something very tiny, times the function phi. Then when you write the non-local mean curvature, think that we integrate on vertical lines, right? So we integrate the kernel on vertical lines, which would be the characteristic function of phi minus the characteristic function of the complement of phi relative to x minus x0 to the n plus s. Yeah? But if I integrate on vertical lines, sort of what I see on this side and what I see on this side, they cancel completely, because one is in the complement and one is outside. So really, in the non-local curvature is very important, the difference between how large is this relative to this, yeah, which is given by epsilon. Epsilon is the band. Epsilon, the difference from this point, with the difference from this point, this is 0. Yeah? If this would be in the middle, if it would be 0, I would get 0. Yeah? So this term twice epsilon k times the top is simply the difference between these two segments. Yeah? What I have on the bottom, I should have on the bottom the distance from 0 to the point. Well, I'm inside here. The distance from 0 to the point where I am. Yeah. But roughly, because it's a very tiny band, the distance in Rn between the points is given more or less by the projection plus a very tiny error. Epsilon is very, very tiny. Yeah? So somehow the bottom I can replace, I can go from the distance in Rn to the projections. Yeah? So what this essentially tells, you can do this in some large ball, and outside of that large ball you say I have some error. Yeah? And what this shows you, it shows you that the mean curvature linearizes to the fractional Laplace. Yeah? Which fractional Laplace? Well, it's the fractional Laplace, so I'm going to say here, is Laplace to the 1 plus s over 2 of phi. Why 1 plus s over 2? Because I went down a dimension. Yeah? These things are in Rn minus 1. This function is defined in Rn minus 1, and here I have power n plus s. Yeah? So the linearization of the non-local minimal surface. By linearization, I mean if you give me a plane, a straight line, and I just wiggle it, I say I still want to solve non-local mean curvature equal to 0 up to error epsilon, then the phi should pretty much solve this equation, this equal to 0. Yeah? And this one has nice estimates. This one has the has C1 alpha, C2 alpha estimates. So this would be the idea, the moral, why it works. However, how do you know that your function really looks like a graph? That's sort of one of the important parts, right? I mean, all you know is initially the boundary of E is between two planes. It can look very wild. I mean, it can oscillate in principle 1,000,000 times. And how do you know that this, in the end, is much thinner and very nice? Yeah. So this has to do with something with Harnack inequality, saying that when you zoom in, you can diminish the oscillation of your E. As you zoom in, and you have to you are well approximated by the graph of a function. Yeah? Okay, so I don't want to go more into detail. As I said, if you look over the notes, you can look for the details. Yeah. Yes.
So and then after some point, the graph, it is the boundary is given by a graph. So
yes.
Then you're sufficiently done it.
Yes. Yeah, so there is this important step of approximating your set E with the graph. So yeah, but once you know it's very close to a graph, this computation tells you that that graph has to be the graph of S1 plus S over 2 harmonic function. And then it's supposed to behave better. I mean, when I go in half the ball, the oscillation really has to decay as I'm predicting, on and on and on. Okay. And sort of the thing, I also have some information outside of this. This is encoded over here because I know that the tails also behave in a certain way. Okay. Okay, so what do we do after we have this, right? So after you get C1 alpha, you can bootstrap that. So once you know you are actually a graph, you can get to C infinity. This is a result of Barrios, Figal, and Valdinocci. And essentially, once you know you are a graph, you can write your equation in some form like this. Yeah. And this looks very much like a nonlinear fractional equation that you have some initial regularity and then you can bootstrap. So something that is not known if actually you can prove that the boundary is analytic. Yeah, so this is not known. So let's say this is an open problem. I mean, I suspect that it is analytic, but often when you deal with non-local equation, this is a bit harder to obtain than the classical sense. Also, one remark is that the constant epsilon 0, this band, the width of the band, can be taken independent of S as S tends to 1. So somehow you also want to recover this improvement of flatness statement is what is known the Georgie theorem for minimal surfaces, saying that if you are sufficiently close to a band, you are C1 alpha. So if you want to recover also the local result, you can do it. Of course, you have to be a little bit more careful to get uniform estimates. Yeah? So in the end, this constant epsilon 0 can be taken independent of S as S tends to 1. But in this case, you really have to use minimality. So one important remark here is that all used in the proposition, all I said that you need to use in order to do this improvement of flatness is the equation, only the equation, nothing about minimality. However, for classical minimal surfaces, if you give me two parallel planes, so if you give me this, let's say if you say that, or three parallel planes, so you think that this is the boundary of E. Okay, let me draw. In the classical, so now I'm no longer in the non-local setting, but I do this picture. So my set E consists of this little band, and maybe all this now. Yeah? So when you look at the boundary of E, it would consist of three parallel planes. Do I satisfy the equation everywhere on the boundary? Yeah, if I'm in the classical setting, yes, mean curvature is 0. These things are straight. Yeah. So in the classical setting, you cannot simply say, well, if I satisfy the equation at all the points, then I'm actually the graph of a function. That's not. You have to use minimality also. You have to say, not only that I satisfy the equation, but I'm minimal. This is not minimal, because you can cut this piece in the middle and get less perimeter just by going on the boundary like this. Yeah? So this is not minimal, but it satisfies the minimal surface equation. While in our setting, we said that this picture is not possible, and the reason why it's not possible is because non-local curvature, when I compute the non-local curvature here, I still feel a bit the outside. Yeah? So this picture is not possible in the non-local setting, but it's possible in the local setting. And that's one difference. On the other hand, if you want to obtain uniform estimates, yeah, if you want to say, I want to obtain estimates that remain true in the limit, then you actually, minimality becomes more important. Okay, so let's move on. Let's see how I'm doing on time. Okay, so once you know that you have some smooth surface, or at least near a point where you want to do the computation, you want to say, how do I want to understand the linearized operator. The linearized operator is, I want to understand if I want to do perturbations of this surface and I still want them to be minimal, or what do these perturbations satisfy, right? So we think that, let's say, the boundary of E is a nice set. The minimal surface is a very nice set. And I take a deformation of it. Yeah? How do I deform it? So from each point X on the surface, I'm going to move perpendicular to it, yeah? By an amount T. T is a very tiny parameter. I want to do only infinitesimal deformation times eta. So eta is a function defined on the surface. Okay, and the question is, how does the non-local mean curvature change when I do this deformation? Yeah? If you look for the classical curvature, mean curvature, the local one, the way the mean curvature changes is that the mean curvature of the new surface is whatever I started at X, but I have, because I do a deformation like T, right? It picks up a first coefficient, which is given by the Laplace of eta on the surface, plus the A squared. A squared is the sum of the principal curvature square, which is the second fundamental form square times zeta, plus lower order terms. So this coefficient is very important, right? Because this coefficient tells you if, when I do the perturbation, it depends on the function eta, right? So eta, you can try to think that eta is the graph. Sorry, eta is the function which gives the graph of your new surface in the perpendicular direction. Yeah? So this would tell you, if I want the new surface still to be a minimal surface, I want this thing to be 0. So this is known as the Jacobi operator. What happens in the non-local setting? Yeah. So if I have a point x0 and I want to say I want to look at the curvature at the at the image of x0 up. Yeah? So how does the non-local curvature change? Well, so what I have to do, actually I have to go back here and translate this surface down for these 2 points to coincide. So I'm just translating it down. So basically I have to translate the whole surface back by this backward vector. Now that the 2 points coincide, I have to look at the non-local mean curvature operator at x0 and see what happens. Yeah? And then the difference, I mean, all I have to pay attention is how much area, after I translate down, how much area remains between the 2 graphs. This would be the change in the non-local curvature divided by this quantity. Yeah? So when you do the computation, I mean, basically you have to take this thing here and multiply it with nu of x, and divide by this. This is what you get. And when you rearrange it, it looks like this, right? It looks that what you get is an integral over the boundary of phi of eta of x minus eta of x0 divided by x minus x0 to the n plus s dx. This is like a fractional Laplace of eta on the surface. Yeah? I measure the distance still, if I take a point x here, I measure the distance still in Rn, like as a straight line, but otherwise it really looks like the fractional Laplace. Yeah? And then I have this plus eta evaluated at x0 times this quantity, which is always positive, which is 1 minus nu of x0 dot nu of x divided by x minus x0. And this morally can be thought as a second fundamental form, if you want to copy the same formula, if you want, in HS. Yeah? I mean, this would be 0 if you deal with a half plane. If you deal with a half plane, the normals always coincide, and I would get 0. But if I'm not a half plane, then it would be positive. Not half plane, half space, sorry. So if the boundary is straight, that quantity would be 0. So it looks very similar to this. Yeah, just okay. Okay, so now let me say a few things about what are the consequences of this flatness theorem. One consequence is the half space is the cone with least energy. If you give me a cone, this monotone quantity is always a constant. So you can say each cone has an energy given by that constant, right? So it says the half plane is the cone with the least energy. How do I know it's the least? If you give me any cone E bar, yeah, I can always find a point away from the origin where I find the ball tangent from one side. When I zoom at this point in more and more and more, I'm going to see the half plane because I'm already pretty regular. Because I have a tangent ball from one side, I can show that there is also a tangent ball from the other. So actually, I'm going to be quite regular near this contact point. So if I look at the energy coming from infinity, right, the energy, if I center the monotonicity formula at the origin and I look on a very large ball, or if I center the monotone quantity at x0 and I look on a very large ball, they are essentially equal on very large balls, yeah, like for radius tending to infinity. However, one of them remains constant when I zoom in. One of them is going to be monotone when I zoom in. Yeah? So when I zoom in, I know that when I come from infinity, I see pretty much the energy of E bar from x0, but when I zoom in, I end up with the energy of the plane. Yeah? So there is an inequality here between them. This is like a classical argument. Yeah? So half planes have least amount of energy, and there is also a dimension reduction argument due to Federer. This is again classical, is that there exists a first dimension n0, which possibly could be infinite. I mean, although not expected to be infinite. for which a non-trivial cone with smooth cross-section exists. Yeah? So the question is, let's try to find these cones. Yeah? It says that up to a certain dimension, I'm just going to see the half plane. And from one dimension on, I'm going to start some other new cones are going to pop up. Yeah? So this first dimension, where another cone pops up, you call it N0. In the case of classical minimal surfaces, this N0 is 8. Yeah? So up to dimension 7, you see only the half plane as a minimizing cone. In dimension 8, there is another one. Yeah? Okay, and then the dimension reduction argument says essentially that the boundary of E is supposed to be smooth all the time, except on a set of dimension n minus this n0. Yeah, so it's very important to find this first singular cone that is minimizing. So what is this first dimension for in our setting, in the setting of non-local minimal surfaces? And let's say all we can say is that in 2D, there are no such cones in 2D. Yeah? But it's not known in 3D, unless S is very close to 1. I'll mention that. So why is this difficult? You start, let's take one possible comparator. I'm in 2D, and I'm looking for, I take the axis, the x-axis and the y-axis, and I'm taking the set E, let's say, to lie in the first and third quadrant, while the complement of E is the other. If I take points on the boundary of E, the mean curvature is 0 by symmetry. Yeah? So this would be, I know that the mean curvature is 0. At the origin, I cannot really check the equation because I don't have a tangent both from one side, but also at the origin, morally, it looks that the mean curvature is 0 because sort of everything is symmetric. Yeah? So is this a minimizer or not? Well, if you come from length, from the classical setting, you know it's not a minimizer, right? If you look at the perimeter, you always know that if you give me a set here, a ball here, it's cheaper to take perimeter like this, to cut out these two pieces, or maybe to add them this way. Yeah? I mean, the length, this plus this, is always less than this plus this. It is always bigger than this and this. Yeah? So, of course, this is obvious into this triangle inequality for lengths. You don't want to have crosses. You can remove crosses and pay less energy. However, in the non-local setting, let's remove these two pieces in the non-local setting, and we suspect that we have less energy. Yeah? Well, you have to say, how do you have less energy? You have to show me that when I integrate all x's in these triangles against all y's in the second and fourth quadrant, and all x's in this against whatever is outside in here, against here and here, right? One is bigger than the other. Yeah? I mean, the length is clear, right? That this plus this is more than that. But if I do integrals, x and y's like this with x and y's like this, it's not so easy how to cancel them. I mean, probably you can show it in this particular setting, but you want to show it basically for all cones. So you can have more slices or other cones. So I'm saying that this is an instance where already the fact that you are non-local is difficult to do computation in the non-local setting. I mean, so something that would be completely trivial in the local. So how do you prove it in 2D? How do you prove this theorem, the regularity of cones? So there is a trick. The trick is to say, well, I want to take as comparator translation of the set E. Yeah, so I have here, I'm going to use the extension. It's not necessarily, I mean, you can do it without the extension as well. But let's say, so I have here the set E, and I translate the set E, the set capital E in a unit direction epsilon. So I have here an epsilon times E. Yeah, so I want to translate it, the vector epsilon small e, like this green vector in some direction. And then I want to do a compact perturbation, so I have to cut off. So I translate it, but somewhere I want to reconnect it back to the original set in B1. Yeah, so here phi is a cutoff function that is 1 in B1 half, but then is 0 outside B1. Yeah? So I create two translations. First I translate to the right by E and then to the left. Yeah? Okay, and I say how much these translations change my energy, by how much. Yeah? And I claim that they only change it by epsilon squared, by something. If I translate by epsilon, then the energy in the extended variable changes by epsilon squared. How do I see that? Well, if I add the energy of U plus and U minus, right, and I do the change of variable formula, the epsilon term cancels, because that's why I'm doing two translations, one to the right and one to the left, so that the first order terms involving epsilon and minus epsilon, they cancel. So I'm left with errors of epsilon squared, right? But U is a minimizer, right? Okay. Okay, U is a minimizer, so on the other hand, each one of these two is bounded to the left by J of U B1 plus. Yeah? So I have their sum is bounded above by 2 times J of U B1 plus O of epsilon squared, bounded to the left just by this quantity, by minimality. Yeah? So it tells you that each individual one, this and this, they are epsilon squared errors in terms of the energy. Yeah? But now what I want to do, I want to take the maximum of U epsilon and U minus epsilon and the minimum. Yeah? So I want to sort of rearrange this sum in this sum, where I replace U epsilon by the maximum between this and U minus epsilon by the minimum between them. I don't change the energy. The energy of the bottom is the same as the energy of the top, right? So in the local setting, if I have two functions, right? In the local setting, if I have two functions, so I have a function here and a function here, right? And I replace, I'm looking at the maximum, and if I'm looking at the minimum, yeah, the energy of the maximum plus the energy of the minimum is the same as the energy of the first plus the second. Yeah, so this plus this is the same as this and this, and in particular, this tells me that also U plus and U minus are just epsilon O of epsilon squared errors with respect to the original surface. Okay, so essentially this tells me that, let's say, if I look at the maximum, U plus, and U, this would be still close enough to the original energy. So here I draw the picture, right? I draw the picture in which I'm looking at a translation of E and E, but then I'm looking at the maximum. So when I'm looking at the maximum in the places where E is 1, or the translation is 1, my new function is going to be 1. So this is what happens with the trace of U plus. However, U plus is not really a minimizer. Well, sorry. So if I hit points like this, if I think that this is U epsilon and this is U minus epsilon, yeah, U plus would be the maximum. So U plus would be this. Yeah. And sort of if U minus epsilon and U epsilon, they cross at some point, then when I look at U plus, this for sure would have some Lipschitz singularity somewhere in the upper half space, and wouldn't be a minimizer. Yeah? And then if I cut a small ball around such a point, such a small ball of radius epsilon, and I replace with the actual minimizer, then I would gain, if this is a ball of radius epsilon, I would get epsilon to the power n minus s. Yeah? So somehow, the fact that U plus, I mean, it depends. If U plus is a minimizer, sorry, if U plus either coincides with U minus epsilon or U epsilon, then I cannot do anything. Yeah? But if the maximum between these two doesn't coincide either with this or with this, then I can change it locally, the energy, and gain an amount like this. Yeah? And I would get a contradiction, right? What is the contradiction? I know at one time, I know that this energy is more or less the energy of U plus this error, epsilon squared. On the other hand, I know I can modify slightly this and get the energy down by this amount. Yeah? But this is much bigger than this. Yeah? So I lowered the energy beyond the minimizer. Where did I use dimension 2? I use dimension 2 here. This is supposed to be an n minus s. Yeah? If I go in dimension 3, I wouldn't get the contradiction because when I lower the energy locally in a ball of radius epsilon around the crossing points, I would only lower the energy by a sigma epsilon to the 3 minus s. Wouldn't get necessarily below the energy of U. Okay, so this is looks like a funny argument. It has very much to do with the growth of the energy at infinity. Yeah? So in low dimension, you have slower growth. In high dimension, you have more growth. And that's why this argument cannot work in all dimensions. Yeah? And not expected to hold in all dimensions. Okay. Are there some questions? So essentially what we do here, we just translate, right? Translate the original set, try to glue them farther out, and here instead, I mean, I change the set by doing the union of E and the translation of E. And that would be the comparator that I show has less energy than the original one. Sorry, so how do I get that only half planes have the energy? Basically, this argument shows that these two functions always have to be ordered. Yeah? So it says that no matter which translation I do, U plus has to be bigger than U minus, right? The only case that happens is when you have half planes. Yeah? If I have half planes, if here I have 1 and -1, no matter how I translate in one direction and the opposite, I always get an ordered between those two translations. But the minute you give me a cone, I can find one direction in which they are no longer ordered, like it's shown in this picture. Yeah? I cannot say that the translation of E is completely included in E or completely included in the complement of E. Or something like this, yeah. So that's how you get to half planes. Okay, so let's say time is pretty much up. Let me only mention one more thing. So if you are very close to 1, it says it's very close to 1, then you can get that the half space are the only minimal cones up to dimension 7. But this result uses the local theory. I mean, essentially say if I know this result for local, so, and then when S is very close to 1, I can prove that I have some convergence to that, and I use the local setting to get this result. And this only when S is extremely close to 1. Yeah. Okay, okay, so let me just skip this these few things here. Okay. And maybe as a last slide, I'll simply say what are some major differences with classical minimal surfaces, yeah? Between the non-local. So one is about stability. Stability means I'm not only assuming I'm minimizing, but I'm minimizing only under infinitesimal perturbations. Yeah? So if you look at this situation in which you have a bunch of parallel sets, E is given by this, and the complement of E like this. Seems like this is a critical point, meaning that at each point on the boundary, the non-local mean curvature is 0, or even the classical mean curvature is 0. If I look at the classical mean curvature, this is stable. If I try to perturb this and I look at the lengths of the perturbations, the length of the perturbation would be more than the length of the original set. Yeah? However, if I look at the non-local curvature, this is not the case. Yeah? So the non-local curvature, if I fix a point up here, it seems locally, when I start integrating, it seems that indeed, because this is curved down, the curvature seems to be pointing downwards. Yeah? But at some point when I start taking larger balls, I'm going to start to see some influence coming from the other perturbations that are of the same order. So at some point, if you have enough of these bands around, maybe one or two, that don't worry, but if you have 100 such bands around, even infinitesimal perturbations, the curvature at the tip would point upwards, meaning that if you try to solve a flow and you just perturb things a little bit, things would be very unstable. I mean, they would break down. Yeah? So this picture is stable for the classical setting, is unstable for the non-local setting. Yeah? That's something that is a little bit unexpected. Yeah? And another major difference is about boundary regularity. Boundary regularity, if you give me very nice data outside, then always the non-local minimal surfaces are going to create, not always, but let's say generically, they're going to create a discontinuity at the boundary. Yeah? That's something, again, that doesn't happen in the local setting. So somehow, why such a discontinuity? Because it doesn't matter so much the local, where I end up here, maybe what matters very much would be like a global picture. Yeah? So if you give me a half plane and you just draw some bumps farther out, this would be on your boundary data, and you try to solve for the non-local minimal surface inside, the non-local minimal surface would pop up and create some discontinuity at the boundary, but would be smooth inside. So the boundary regularity is different. And let me just leave like this with some open questions. So this would be classification of minimal cones, let's say even in the dimension 3. What you can say about this. Study of singularities for the non-local mean curvature flow, and some construction of some special solutions. Yeah? So I mentioned a few of this yesterday in the afternoon. So I'll stop here. Yeah.